In this lecture, I'm going to continue talking about the substitution rule, which is a really important integration technique. So we're going to start by talking about a few more examples where we use the substitution rule to solve indefinite integrals. So here we're looking at finding the integral of tangent of x, which I said was one of the trig functions we were going to learn how to integrate in this section. Notice that looking at this right away, it might not seem obvious that the substitution rule would be helpful, but if we rewrite tangent as sine x over cosine x dx, then we can see that one of these functions is the derivative of the other, so we're going to be able to pick here, we would use u equals cosine x, so that its derivative up to a constant here is appearing next to it in the integral. So if we do u equals cosine x, then du would be negative sine x dx. So we can say that negative du is equal to sine x dx. So I can go over here and say this is the integral of 1 over u, and then sine x dx gets replaced with this negative du. So now I'm looking at integrating 1 over u du, and I know that my integration rule for that is the natural log of the absolute value of u. Okay, so once I've done this piece of the integral, I have negative the natural log of the absolute value of u plus c, and then I would replace u with my cosine x. So I get this rule that the integral of tangent x is negative the natural log of the absolute value of cosine x plus c. You may notice that this is also written in another form on your handout, and that's because we can use log properties here to say that this is the log of the absolute value of cosine x to the negative 1 plus c, which means this is the log of the reciprocal of this. So this is the log of 1 over cosine x in absolute value. Or maybe I should just say, 1 over the absolute value of cosine x. And we know that 1 over cosine x is secant x, so that's what we're going to replace this with. So I've got log of 1 over the absolute value of cosine x, which is the same as log of the absolute value of secant x. So both this form and this form are antiderivative of tangent of x. Okay, so computing the integral of tangent as well as the integral of cotangent x, we'll use the substitution rule. So I'd recommend trying the integral of cotangent x on your own. Okay, so let's look at one more example of the substitution rule with an indefinite integral. Here I've got the integral of x over 1 plus x to the 4th dx. So this is one that is a little bit trickier, so I wanted us to see one that's not maybe as super straightforward as some of the other ones. Here you might initially think I should let u be 1 plus x to the 4th, but then your du is 4x cubed dx, so you've got an x dx here, so that doesn't seem to be very helpful. So if you look at this, you might have to play with it for a little bit, but one thing that I did looking at this, sometimes it's helpful to rewrite things in terms of other powers. So we could rewrite this as x over 1 plus x squared squared, and realize that x to the 4th is actually just the quantity x squared squared. And then I notice that there is a relationship here between this x squared and x, so that if I let u be x squared, a little bit thicker line than I wanted. But if we let u be this x squared here, we are going to be closer to getting what we would like. So let's go down here. So let's let u be equal to x squared. So then du would be 2x dx. So this is going to give us 1/2 du is x dx. So this is a little bit of insight to rewrite this x over 1 plus x to the 4th in this way. And this takes practice to recognize here that the substitution will not be u equal to this whole thing in the denominator, but be equal to this little piece here. So as you do more and more examples, you start to see what good choices for u will be in different situations. So here my x dx is going to get replaced by that 1/2 du, and then I have 1 over 1 plus u squared. So I have 1/2 the integral of 1 over 1 plus u squared du. So here I have to remember my antiderivative rules and remember that the integral of something of this form is my arctangent. So I have 1/2 arctan of u plus c. So this gives me 1/2 arctan of x squared plus c. Okay, so now we've gotten a little bit more practice with our substitution rule in indefinite integrals. So we want to move on to talking about the substitution rule for definite integrals, which introduces another step into our problem, because not only do we have to change our integrand to being in terms of u, but we also have to change our limits to being limits that are in terms of u. So just to review here a little bit, if we have our function being a differentiable function whose range is an interval I and f is continuous on that interval, then for indefinite integrals we can rewrite our integral of f of g of x, g prime of x, as an integral of f of u du, which simplifies the step of finding the antiderivative. When we are talking about a definite integral, so I'm interested in computing the integral from a to b, so these are some sort of x limits here, meaning we're going from x equals a to x equals b of f of g of x, g prime of x dx. Then I'm going to again let u be equal to g of x, so that my limits here are no longer going to be from x equals a to x equals b, but from u equals g of a to u equals g of b of my function f of u du. So we're going to have to see how this looks in some examples, but what we're going to have to remember in these using the substitution rule for definite integral is that we're always going to want to change our limits to be in terms of u, so that we get this new integral where everything is in terms of our new variable u. Okay, so let's see how this goes in an example, and then we'll see geometrically how the example here, where I've got my limits in terms of x, corresponds to the limit, the integral where my limits of integration are in terms of u. So here I'm interested in taking the integral from 0 to 2 of 2x over x squared plus 1 quantity squared dx. So I'm going to use substitution here. I see that the inside function of the more complicated piece is this x squared plus 1, so we'll let u be x squared plus 1, so that du is 2x dx. So I see that 2x dx there. So I've got this integral of du all over x squared plus 1 squared, so that's all over u squared. Now I also need to change my limits. So initially I have limits that go from x equals 0 to x equals 2. When x equals 0, u is equal to, remember u is equal to this new function g of x, so u is equal to g of 0, which would be equal to 0 squared plus 1, using that definition that I have of u. So when x is 0, u is 1. So in the position where I have x equals 0, I'm now going to have u equals 1. When x is 2, u is going to go to g of 2, which means 2 squared plus 1, again using my definition of u as x squared plus 1, which is 5. So when x is 2, u is 5. So we're looking at this integral from 1 to 5 of u to the negative 2 du, just to rewrite this using our negative exponents instead of as a fraction. Now what I have to remember here is this is now the integral that I'm computing. I'm not going to go back to x. I've got this new definite integral. Wait for my writing to catch up here. This is our new definite integral. Right here, that is equivalent to our question. We now compute this integral without ever going back to x. Okay, so I'm emphasizing this because we know that when we were working with indefinite integrals, so let me just contrast this with our previous example. With our indefinite integrals, I did have to get my antiderivative in terms of u and then convert it back to x, but that's because our indefinite integral here has to be a function and it should be in terms of the variable that we started with. However, with our definite integrals here, I'm looking for a number. I've now said that the number that represents this integral from 0 to 2 of 2x over x squared plus 1 squared is the same as the number that represents the integral from 1 to 5 of u to the negative 2 du. So now I'm just computing this integral. So I have u to the negative 2 plus 1 over negative 1 evaluated from 1 to 5. So we're looking at negative 1 over u evaluated from 1 to 5. So we plug in 5 first, so we've got negative 1/5 minus negative 1 over 1. So we have 1 minus 1/5, and we get 4/5. So 4/5 is the answer for the integral from 1 to 5 of u to the negative 2 du, and it's equivalent to the integral from 0 to 2 of 2x over x squared plus 1 squared dx. So let's see how this variable change and integration change refers to an area under a curve. So if I look at these two different curves that I have here, the first one is y equals 2x all over x squared plus 1 squared. And so the original integral that I'm interested in here is the integral from 0 to 2. So that would be the area under that curve from 0 to 2. So this is the integral from 0 to 2 of 2x over x squared plus 1 squared dx. Okay, I've shown that that area, that blue shaded region, is equivalent to the area under this other function here from 1 to 5. So that new shaded area here is the integral from 1 to 5 of 1 over u squared du, and those are both equal to 4/5. So by doing this little variable transformation and transforming our limits shows us that we have this new easier to integrate function that when we look at its area between 1 and 5, we get the same area as the original question that we're interested in. So computing this integral is much easier, so we're going to compute this equivalent easier integral. Okay, so this is what we're doing when we're changing our integrand and changing our limits here. We're getting this new function that we can integrate that gives us an equivalent value. So let's get some more practice with that and some more examples. So here we've got the integral from 0 to 2 of x cubed times the square root of 16 minus x to the 4th dx. So we'll let u be 16 minus x to the 4th. So du is negative 4x cubed dx. So that's pretty close to what I have here. I've got x cubed dx. So I'll divide both sides here by negative 4 so that I get x cubed dx by itself. So I'm going to have this integral of negative 1/4 du, and then I'll have the square root of u, because u is going to replace this 16 minus x to the 4th. So now I just need my new limits. So when x equals 0, u is going to be 16 minus 0 to the 4th, so u will be 16. So when x is 0, u is 16, so I put 16 in the same spot that 0 was in for x. So x equals 0 goes to u equals 16. When x is 2, u is equal to 16 minus 2 to the 4th, so that's 16 minus 16, or 0. So when x is 2, u is 0. Okay, so notice that this does make us have an integral where I'm going from 16 to 0, so 16 is bigger than 0. And it would be perfectly fine for me to go through and just compute this integral in this way. The answer will come out correctly, come out equivalent to this integral from 0 to 2 that I'm interested in. But it might simplify my work a little bit, make me not have so many negative signs show up, if I reverse the order of these limits, and when I do that I multiply by negative 1. So this would be equal to 1/4 times the integral from 0 to 16 of u, I'll make that a fractional exponent now, u to the 1/2 du. Okay, so we can switch the order of these limits as long as we multiply by negative 1. So both of these two integrals here are equivalent to what I was originally interested in finding. So now I've got 1/4 u to the 1/2 plus 1, so that's to the 3/2, divided by 3/2 or times 2/3, and evaluated from 0 to 16. Okay, so we're going to have, let's see, this is 2 over 12, so that's 1/6 u to the 3/2 from 0 to 16. So we plug in 16 first. So we have 16 to the 3/2 minus 0. Okay, so the square root of 16 is 4. 4 cubed is 64, so we have 64 over 6, or 32/3 is the answer to this integral. So again, notice that when we changed our limits to these u limits, and we did our problem all in terms of u, and we never went back to those x limits from 0 to 2. We got this completely new integral, and then we solved that new integral problem to get our numerical answer to the problem. Let's look at another one. Here we've got the integral from 0 to 3 of v squared plus 1 over the square root of v cubed plus 3v plus 4. So what's in the denominator is fairly messy. So we're going to let u be v cubed plus 3v plus 4. So du will be 3v squared plus 3. I want to put parentheses around that, dv. Okay. So what I have in my integrand is very similar. I've got a v squared plus 1. So if I factor a 3 out of this, I'm going to have 3 times v squared plus 1 dv, and then I could divide both sides by 3. So I have 1/3 du is v squared plus 1 dv. So this will be my integral here of 1/3 1 over the square root of u du. Okay, because the 1/3 du is replacing this part, and u is replacing this piece under the square root, so I just have 1 over the square root of u. So now I need to change my limits. So when v is 0, u is 0 cubed plus 3 times 0 plus 4, which is 4. So v is 0 gets replaced by u equals 4. And when v is 3, u is 3 cubed plus 3 times 3 plus 4. So that's 27 plus 9 plus 4, so we get 40. So we've got this integral from 4 to 40. So we have 1/3, the integral from 4 to 40, of u to the negative 1/2 du. So we use our antiderivative rule, so u to the negative 1/2 plus 1, that's 1/2 divided by 1/2, or times 2. And we need to evaluate this from 4 to 40. So we're going to have 2/3, the square root of 40 minus the square root of 4. And so anything else that we do is just to simplify this, make it look a little bit prettier. So the square root of 40, that's 4 times 10, or 2 square roots of 10, and the square root of 4 is 2. We can factor out that 2, so we've got 4/3, the square root of 10 minus 1 is our final answer. Okay, so notice the process that we're doing, and we're always showing all of this work and using our equal signs and keeping our differentials there, changing our limits, showing our work over here with our new limits, and getting it down to our final answer. Okay, so we just want to look at a couple more examples, to see a few more types. So here I've got one that involves our sine and cosine functions. So I've got an integral from 0 to pi/4 of sine of theta over cosine cubed theta d theta. So I've got this cosine cubed thing in the denominator, so I want to let u be the inside of that cubed function. So we'll let u be cosine theta. So du will be negative sine theta d theta. So I'm going to have negative du is sine theta d theta. Okay, so this replaces some of what we have here. Sine theta d theta is going to be that negative du, and cosine cubed theta will be 1 over u cubed. Okay, since that cosine cubed is in the denominator. So now I just need to deal with the limits and use what I know about exact values of trig functions. So when x is 0, or excuse me, this is not x here, when theta is 0, u is equal to cosine of 0, which is equal to 1. So when theta is 0, u is 1. When theta is equal to pi/4, u is equal to cosine of pi/4, which is the square root of 2 over 2. So we're going from 1 to the square root of 2 over 2. Okay. I have this negative sign out in front. If I switch the order of my limits of integration and multiply by -1, I can have the integral from the square root of 2 over 2 to 1 with a positive sign out in front. So switching the order multiplies by -1, and then this is u to the -3, written using negative exponents instead of as a fraction. So I anti-differentiate that, so I have u to the -3 plus 1, or -2 over -2, evaluated from root 2 over 2 to 1. So this is -1 over 2u squared. I find it a little bit easier to excuse me, evaluate if we now rewrite that not as a negative exponent, but put it in the denominator. And so I'm going to plug in that 1 first. So we have -1 over 2 minus -1 over 2 times the square root over 2 squared. So if we square root 2 over 2, that's 2 over 4, or a half. 2 times a half is 1. So we're going to have minus a -1, or plus 1. So that gives us a final answer of 1/2. Okay, so this was similar to a lot of our other ones. We had to pick a u for our inside function. We had to change our limits. We got this new function in terms of u, and then we evaluated it using our antiderivative rules, together with the fundamental theorem to plug in our limits. Okay, so maybe just a couple more to look at. Let's see. I've got a bunch more for us. Just want to make sure we see all kinds of different types. So here we've got the integral from 0 to 1 of x e to the -x squared dx. So we would let u be -x squared. So du would be -2x dx. So I'd have -1/2 du equals x dx. So x dx is this -1/2 du, and then I have e to the u. When x is 0, u is -0 squared, which is just 0, so that one stays the same. When x is 1, u is -1 squared, or -1. Okay. So again, if I want to reorder my limits, switch the order of my limits, I'd have to multiply by a negative. So instead of having -1/2, 0 to -1, I'd have +1/2, the integral from -1 to 0 of e to the u du. And now I know the antiderivative of e to the u is e to the u. So I'm just evaluating that from -1 to 0. So this is going to be e to the 0 minus e to the -1. So we'll have 1/2 1 minus 1 over e. And we can leave it like that, or we could write it as e minus 1 over e inside by getting a common denominator. And then say we have e minus 1 all over 2e is our final answer. Okay, so we want to make sure that we know how to work with our exponential functions, log functions, polynomial functions, all these different kinds of functions in terms of finding the antiderivatives. Okay, so what about something like this? So I wanted us to see that a couple that look a little bit more complicated. So here it might not be immediately obvious what you need to let be your u in your u substitution. But notice if I pick u to be the denominator, the derivative of the denominator will be the numerator. So we'll let u be e to the z plus z, so that du is e to the z plus 1, put that in parentheses, times dz. So I have this integral of 1 over u du. So this part up here, e to the z plus 1 dz, that becomes my du, and then I have this 1 over e to the z plus z, or 1 over u. So I just have to deal with my limits. So when z is 0, u is e to the 0 plus 0, which is 1. So when z is 0, u is 1. When z is 1, u is e to the 1 plus 1, which is just e plus 1. So don't worry if your limit ends up being something that involves e or pi or some sum of a couple of different things. So here we need to use that our antiderivative of 1 over u is the log of the absolute value of u. Always write the absolute value bars in your work, even if when you evaluate you won't need it. At this stage I still just need the general antiderivative. So I need to say the natural log of the absolute value of u, and then that's evaluated from 1 to e plus 1. So this is the log of e plus 1 minus the log of 1, and now I can drop these absolute value bars because e plus 1 is always positive, and I know the log of 1 is 0. So I just have the natural log of e plus 1 is my final answer. Okay. Sometimes you would lose credit if you don't simplify something like this, because we are expected to know that the natural log of 1 is equal to 0. Okay. So here's my last example, and I wanted us to take a look at this because we have to use a little bit different substitution technique. So here, our more complicated thing is what's under the square root, so we would let u be 1 plus 2x, so du would be 2 dx, so I'd have 1/2 du equals dx. But this is an issue because I still have this x that's up here. So I've got, this 1 over a square root of u, but how am I going to deal with x? Okay, well dx I can replace with 1/2 du, but somehow I need x in terms of u. So let me just write it like this. Normally we won't write something that's mixed with x's and u's, but just to kind of illustrate what we're thinking, we need x in terms of u. And if I look at what I have here, well, u is equal to 1 plus 2x. Well, that's a little linear equation, so I could solve for x. So we'll see that in certain situations, we'll have to do a substitution where we replace some expression with u, and then we replace x with some expression in terms of u. So I see that u minus 1 over 2 would be equal to x, so that I could rewrite this integral, I'm going to need some limits here, as u minus 1 over 2 over the square root of u du. So I'm replacing x with this expression in terms of u. And now I just need to replace my limits. So this was just kind of our thinking, this part that's in parentheses. This is where we really start. Okay, so I just need my limits. So again, when x is 0, u is equal to 1 plus 2 times 0, or 1. And when x is 4, u is equal to 1 plus 2 times 4, or 9. So I have this integral from 1 to 9. So then I just need to kind of clean this up a little bit. So this is from 1 to 9, u minus 1 over 2, so I can bring that part out front. And then this is over the square root of u. Okay, so I just need to do a little bit of algebra now. So this is like a problem we might have had before learning the substitution rule. I want to make that u over the square root of u minus 1 over the square root of u. So u over the square root of u using exponent rules is just going to be u to the 1/2. And then 1 over the square root of u would be u to the negative 1/2. So I have this du. So now we have 1/4, and I need to do my antiderivative. So this is u to the 1/2 plus 1, so that's 3/2 divided by 3/2, which is times 2/3, minus u to the negative 1/2 plus 1, so that's 1/2 divided by 1/2, or times 2, and we're evaluating this from 1 to 9. So we've got 1/4, 2/3, 9 to the 3/2 minus 2 times the square root of 9, minus 2/3 minus 2. Okay, so that's going to be a bit of arithmetic to do, but if we work that all out, we should get the answer is 10/3. Okay, so I've gone through and tried to work several different substitution examples so we can have a little bit more time to practice other examples in class. Please let me know if you have any questions.